Right, I believe I am live online. So welcome everybody to short circuit current calculations and equipment evaluation. And for those of you on WebEx, everybody should be muted. For those of you who are watching on YouTube, I'm going to fade into the intro. Okay, so we are ready. I believe we are ready. Remember to use the chat session. We have a lot of people I think are going to be dialing in. Again, registration for this is pretty high, so which is a good thing. We're all sort of working remote probably these days, so might as well learn something, right? Okay, so I am going to be talking about short circuit current calculations, and let's get this program going. All of your microphones should be on mute, and hopefully, if you're not on mute, check that little microphone symbol just to make sure, because we just want to make sure that everybody is not clobbering on top of others. It'll make everybody's session here a lot more palatable. So everybody should be on mute. Remove your mouse around. You can find the chat session. Let's leverage chat as much as we can to communicate. If you have any questions, please put it there. You'll find a little symbol that looks like a little bubble up somewhere on your screen. When you click it, you'll get a window that sort of looks like this. That's on the screen right now. That has chat, and you'll see where it says to everybody. You could chat amongst yourselves. You could chat directly with me, or you can chat something to everybody. I do hear a microphone, so if somebody's not muted, please mute your line. And you can just enter the information in there and send a note. So let's try that real quick, just to watch the chat, just make sure everybody's engaged. Can you give me, I don't know, say your name, or not say your name, but type your name or type something. We got Scott. Excellent. Jason Moore. Excellent. Okay, so everybody seems like we're fine. Brian Holland's online too. It's our NEMA field rep, Southern field rep. If you ever have a chance to watch one of Brian Holland's presentations, you wouldn't want to miss that. Excellent. We got David A's online. Excellent. We got a lot of good Eaton people. We got Jeff Fecteau. Excellent. Jeff's a good UL person. So there's the other thing about this chat session and about what we've got going on here. Remember, we've got a lot of really good people on this call. We've got UL, NEMA, and other. There's even some other manufacturers in here. There's other consultants. There are a lot of people online that can contribute and answer some of the questions you might have. So please feel free to use the chat session. And I see the YouTube. We've got New England. We got Carlos. We got a bunch of people on the YouTube streaming. So that's great. Let me know on YouTube. Let me know how the streaming is going as well. I've got a little error that's coming up. It says YouTube is not receiving enough video to maintain smooth streaming. So this is like the second time that I've ever streamed, and I'm doing streaming and WebEx at the same time. So, okay, so I am going to try not to look at chat all the time because it can be distracting. When I see questions and I want to answer them, I'm going to try to peek at the chat session and pick up questions. If I don't get to answer a question, I will do that later. I apologize if anybody was on the call last week. I wasn't able to. I exited WebEx. I didn't realize you had to save everything before you exited out of WebEx. I thought it automatically saved it, and it did not. And I didn't record it, or I tried to record it, but the audio and everything got all screwed up. So in any case, I wasn't able to, if there were questions in there, wasn't able to get to them. Technical difficulties. I won't make that mistake this time. And those are online. Again, this is being live streamed on YouTube. You can watch it later as well, because it will be posted on my YouTube site. Please subscribe to that, and then you'll be able to get to all those videos and others as well. Last time I watched the news, I think we're going to be doing more of this. The first thing I'm going to do is, a lot of you went over the quiz, which I thought was awesome. I really appreciate the effort on the quiz. I'm going to walk through the quiz results and tell you which ones, in my opinion, were the right answers and which ones were, I think, the wrong answers. You might be surprised on some of the answers here. I'm not going to get into the details of why they're right or wrong right now, because a lot of that will be covered in the material that we're going to go through for the next 2 hours here. So let's walk through the quiz. The first question was, which of these does not contribute fault current? And we had 75 respondents. Thank you very much to all 75 of you. 12 said generators, 12 said motors, 48 said transformers, and 3 just didn't know. I appreciate those 3 for being honest. The right answer here was transformers. Generators and motors can contribute fault current, but transformers sit out in the they are actually an impedance, and we're going to be talking about impedance because impedance is very important to understand as we walk through available fault current. So the right answer to that was transformers. The first step to calculating short circuit currents is to and it looks like everybody outside of one person who wasn't sure, you fell into one or two different buckets. Either you get the utility fault current data first, or you secure an accurate one-line diagram. And you'll notice I had secure a one-line diagram and then secure an accurate one-line diagram. Thank you for noticing the difference there. 52 of you, I believe, in my opinion, and again, this is my opinion, the one-line diagram is the most important thing you need to secure first, and for a very important reason. I can't really go to a utility if I may have multiple utility sources on a facility depending upon the size. I may have only one, I may have 2. The one-line diagram is going to give me the overall picture. So, and we'll talk about the one-line diagram as we go forward. Maximum available short circuit current on the secondary of a 1000 kVA transformer. Now, here was the trick here. So we had 20 that were clueless, and 6 of you were in the 3 and 12, and 3 at the 10. I'm not sure if those were just guesses or if you actually did the math. But the 23.24 kiloamps was the right answer to that one, and we're going to go over this again in the class, but I'll just say that the 34 who answered 20.92 just took the 5.75% impedance on that transformer and used it. The 16 who put the 23.24 took 5.75 and reduced that by 10%. And we'll get into the reason you reduce that by 10% as we move forward. And probably a lot of those the 35 are probably going, oh yeah, I get it, I understand it. But again, we're going to go through those details if you don't quite understand where that minus 10% came from. We got 42 people on YouTube, which is awesome. All right, so maximum fault current you can see at the secondary of a transformer with the full load amps of 1804 and an impedance of 5.75. 21 said they don't know, which we're going to dispel, and at the end of this, we're going to help you guys understand how this calculation is done. But the 21 that said that you don't have enough data, actually you do. If you take the full load amps and divide that by the impedance, and remember, you've got to use the impedance minus 10%. So those 34.86, those 8 individuals were right across the board. Not only did they know exactly that you can use full load amps divided by impedance to get the maximum about the infinite bus short circuit current on the secondary of that transformer, but they also knew to use 10% less of the 5.75%. So, and again, we're going to go over that a little bit more, but that's a good thing. So to reduce fault current at the end of a run of conductor, I can add another conductor in parallel. 24 said true, 48 said false, 3 said they are lost. So here's the thing. From a impedance perspective, got to remember, resistors in parallel, this is a basic fundamental that we probably all had either in school or in our JATC curriculum. Impedances in parallel will cut the overall impedance in half. So if I have two 10 ohm resistors and I put them in parallel, the equivalent impedance is 5 ohms. And what happens when you reduce impedance? If I put two conductors in parallel, I take the overall impedance of that circuit and I cut it in half. If I reduce that impedance and I cut it in half, then I am actually increasing fault current. And I put this question in here because I asked that question to a class that I was doing in, I don't know, this was a while ago, and I had a lot of people in the audience, and I gave an example of I have a panel board on one wall and another panel board on the other wall, and I had, instead of going down 2 floors and up 2 floors because the engineer said I need 100 foot of conductor, I realized that, I got a drop ceiling here, I can just run a conduit and cut that distance of that conductor way down, save money in copper. But when I do my short circuit calculation, I realized I was exceeding the short circuit current rating of the equipment at the end of that run. And I asked everybody, how would you fix that? And somebody said, well, I would just put another conductor in parallel. And I had 50% of that class say, yeah, that would solve that problem. But in reality, if you put conductors in parallel, that will exacerbate that problem because it will increase the fault current, which is ungood. And that's a new term. You probably learned it today, and you remember where you heard it. I learned it from Tim Cernko. Ungood, I think he got that from Palmer Hickman, but ungood is a new term. I'm sorry? All right, so reduce the fault current. So if you increase the length of the conductor, you can reduce it. In series, in parallel, you will increase fault current. So the 50, all right, we're going to need to figure out how to, please mute. Who is that?
Mándele un correo a María P. Andrés, me copien. Les dice, vean, disculpen por la jodera, pero necesito, por favor, bueno,
I can hear somebody speaking in a foreign language. Please mute your phone. Can't see who it is. Come in. All right, get back to this. Okay, so decreasing short circuit current at my equipment will always reduce incident energy. And that is not true either.
En forecast, por eso mismo.
Have to figure out how to. I'm going to stop the slideshow real quick. And I am going to mute everybody.
Hello.
Stop sharing. Give me a second.
Okay, man.
Mute all. Okay.
Yo estoy en mute, qué raro, man.
I've muted all, but I'm still hearing people. I need whoever that, man. Sure how to mute people here. Okay, well, let's do this. I'm going to go back to the program. And let's take a look at the next question. So decreasing short circuit current at my equipment will always reduce incident energy, and that is not true because decreasing fault current can give me a longer clearing time in arcing current, which will increase incident energy. So actually decreasing short circuit current at your equipment could increase incident energy. All right, so I'm going to share my screen again. There we go. We should get the screen back for the guys who are on WebEx. Okay, short circuit current rating of a fuse is most often greater than that of circuit breakers. So let's talk about that one. 58 said true, 16 said false. Now, I will say that you will probably be upset at me when I tell you that I gave you a little trick question. And the reason is circuit breakers and fuses do not have short circuit current ratings. Circuit breakers and fuses have interrupting ratings. So a circuit breaker and a fuse stop the flow of current, and equipment have to hold it together to let current flow through it. And we're going to talk about the differences there. That is a very big misunderstood topic, which I have a bunch of slides on, but the right answer there would be false. So 16 people got it right, 58 people did not get it right, and 4 need some help here. You're the reason we're here, buddy. All right, so the answer to this was really false, because circuit breakers and fuses have interrupting ratings, not short circuit current ratings. Now, you can use up, over, and down method with current let-through charts to protect busway and establish high short circuit current ratings for that equipment. I had 20 say true, 14 say false, 15 not sure, 29 is what is up, over, down. And that's interesting, which I have some slides on that as well. The right answer here is true. You can use this tried and true method to protect equipment of up, over, and down, but we're going to get into the details of when you can and when you can't use that method to establish a short circuit current rating on a piece of equipment. So the right answer on that one is true. The short circuit current rating of an industrial control panel equals the interrupting rating of the breaker inside. And 22 people said true, 46 said false, 10 weren't sure. So the right answer to that is false. A lot of people, and I've heard people ask about the equipment AIC rating, which is an older term. AIC stands for amp interrupting current, and just that term interrupting should help you understand that that's really the overcurrent protected device interrupting rating. That's not the equipment short circuit current rating. We're going to learn more about the short circuit current rating in this program and what that means. So the right answer here is false, because it takes a lot more than just knowing what the interrupting rating is of the devices inside. It's a process. And this is sort of the breakup of the 78 people or so. I think it was about 78 people that responded to this. 45 are electrical engineers, 20 electricians, 5 mechanical engineers, 3 non-technical people, although I believe one of those 3 was on the phone with me when they answered that, and I know he is not a non-technical person. He is an electrical engineer. Might be watching this. I don't know. And then other are 15. So in any case, so that was the breakout of that program, of the quiz, and I am going to now get back into presentation mode, and we're going to walk through the program. The first thing I want to do is just talk a little bit about the up, over, and down method, because amp interrupting capacity. That's right. Yep. Thank you, Joseph Pavia. Another one of our field application engineers. Again, a lot more people on this phone that are smarter than me. That's why I use that chat session and chat to everybody for that type of information. So thank you, Mr. Pavia. Amp interrupting capacity. Yeah, I think that was from him. Anyway, let's take a look at this this current limiting chart. When we talk about up, over, and down, what we're referring to is this I guess you'd call it a curve that's right here on the left-hand side of your screen. And what you have here, this is across the bottom is your symmetrical RMS amps. Across the bottom, up the side is your peak let through, And the waveform that's over here on the right sort of shows you the short circuit current. Now, here's the thing you got to remember. That first half cycle of short circuit current is a doozy. That's the one that that really gets you. I'm hoping people can hear me online, so I think it can. So I'm seeing some notes on here about sound, so again, I gotta keep my eyes off of that. But remember, this does have audio. This program does have audio, so if you can't hear me, most people can. If you can't hear me, please, you've an issue on your side. So you have a current limiting table here this graphical representation of the capabilities of the fuse. So each fuse will have a curve like this, and any current limiting device, UL requires us to publish this information when it's listed and labeled as a current limiting device. So in this case here, we've got an 800 amp fuse, and we have 198,000 amps of available short circuit current. You'll see this up here on the right hand side of the screen, and that number is represented. That's the peak. My RMS current is actually about 86,000 amps of available RMS. So that's this number right here. 86,000 amps. You'll see that on the top right hand side. That's my RMS root mean square of that available short circuit current. And how we use this table is we want the couple critical parts of this waveform. We want to know what this peak current is going to be. We always talk about short circuit currents. Whenever we calculate short circuit currents, we'll calculate an RMS value of fault current. That doesn't tell us what the peak is. We'll use multipliers to get into the ballpark, because the peak of that current is going to be dependent upon what we'll call the X to R ratio, which you're going to learn about over the next 2 hours. But that X to R ratio is going to tell us what that peak current is and the slope of this leading edge of this fault current. And so that is a very important data point that we need to know, is what is that peak current that's going to be passed through. And then based upon the current limiting nature of the fuse or circuit breaker that's current limiting device, that device is going to act to open the circuit, interrupt the fault current, and it's actually going to reduce that peak current to something lower. And what that something lower is will be dependent upon the performance of the overcurrent device and this chart, or this graphical representation of that performance for each of those overcurrent devices. So for this specific 800 amp fuse, or 86,000 amps of RMS fault current, I use the up, over, and down method to determine what the new RMS fault current that is let through. What is my new RMS value that I could compare for the rating of a downstream piece of equipment? Because we rate equipment in RMS current. So if I tell you that my busway has a 100,000 amp short circuit current rating, I'm telling you that that is an RMS value of a rating. So to get the RMS current that this fuse will let pass through based upon its performance, I start at my fault current, which is down here at 86,000 amps. I go up. That's the up part of up, over, and down. This diagonal line is what we call, that is my current limiting nature of the fuse. I go up to that value, I go over to the AB line, and I come back down, up, over, down, and this value, a little over 20,000 amps, which translates to be about 21,000 amps over here on the side, my RMS let through current for this fuse, when it sees 86,000 amps of RMS short circuit current, is going to be 21,000 amps. Now, if I am permitted technically for the equipment to establish from a protection perspective, to establish the level of protection I can provide to that equipment, as long as my RMS let through is less than the short circuit current rating of that downstream equipment, I can say that I'm I'm limiting the current and providing the protection. Now I can do that sometimes. I can't do it all of the time. And I'll explain that too. But that's what up, over, and down means. It means I'm taking an actual RMS current that a fuse would see in a circuit, and I'm going up to the current limiting portion of this curve, over to the AB line and down, and whatever that lower number is, that is the new RMS let through current that fuse will let the downstream equipment see. Now, another value that is used in some of UL standards and whatnot is the peak let through. So that's this peak value up here. If I go up and just go over, I know that I'm reducing that peak. So if I take the 86,000 amps, I go up to the AB line and over, my peak, this peak value, without a current limiting fuse in the picture, that peak would be upwards of 200,000 amps based on this curve. I go from erase all this, I go up to 80,000, I hit the AB line, I go over to a little less than 200,000. That tells me without a current limiting device in there, my actual peak is going to be about 198,000 amps. Because of the current limiting fuse, my peak current is only going to be around 49, about 50,000 amps. So I'll reduce it from 198,000 amps of peak current to about 50,000 amps of peak current. And I have a video to show you what that means physically in the system. But by reducing the peak, I reduce the magnetic forces on all of my equipment. So when I take my peak value and I take it down to some lower number, I'm reducing the magnetic forces on my equipment. When I reduce the amount of time I let that waveform flow, I'm reducing the heat in my system. So instead of seeing a very high fault current, I'm seeing a much smaller portion of the waveform, which reduces magnetic forces and it reduces heat in the system. That's what, when we refer to up, over, and down, and what we use this for is to establish whether or not we're providing an ample level of protection for equipment for these very high fault currents. So busway is one good example of when I can use up, over, and down, because busway is a static device. Busway is something that delivers current downstream, and my good friend Tim Cernko always called it a high efficiency fault delivering system, because busway is a very low impedance, and we know that when we have low impedance, we are delivering more fault current. So we'll use busway in tall buildings as risers. We use busway in manufacturing facilities, and we use busway in many types of applications. But so if I have a label that says, it'll tell me what the busway is rated for and what the short circuit current what the short circuit current rating is of that, and I can use up, over, and down with other types of solutions to make sure that I'm protecting that equipment at its RMS short circuit current rating. So, again, leveraging the up, over, and down method can be used in some scenarios. I can't use it if I have a circuit breaker in this circuit or something that will become dynamic and also try to interrupt the circuit at the same time as the fuse is interrupting the circuit. So static devices like busway, terminal blocks, things of that nature, I can use up, over, and down to show I'm protecting it. Dynamic devices like circuit breakers, I can't. I have to use a tested method to establish whether or not I'm protecting that equipment. So, and that would be your series rated type of solutions, and we're going to talk about those as well. So that hopefully that gives you just a little flavor for what we're talking about in that regard. So okay, so now let's talk about short circuit currents. All right, what are short circuit currents? When I think about a fault current, I like to use the dam example. When you have a reservoir of water that's being held back by a dam, water is going to be let from the reservoir down to the stream downstream, and that's usually done through. In some cases, there's a power plant down at the base of that dam, and when all of the water flows where it's supposed to flow, it it will stay in its path, its normal path. And when current stays in its normal path, it's restricted, it's managed by the dam system. But if my dam breaks and I have current that goes outside of the normal path, that is a catastrophic failure of the dam, and the reservoir unleashes its power to everything downstream. So, and it can be very destructive. Obviously, I mean, it'll take towns out. It will because of the amount of force, and the amount of force is going to be determined upon how much water I have up in that reservoir. So, and that's very much similar to an electrical circuit. If I think about an electrical circuit, I have conductors, I have panel boards that are delivering power to loads, and if all of the current stays in its normal path, the load will dictate how much current's flowing. The conductors will all be sized to handle the normal flow of current. The overcurrent protective devices will let that current flow, and everything is copacetic, so to speak. So in this example, with all of these resistances plus the resistance of the load, this circuit will draw about 20 amps, about 19.93 amps, based upon the voltage and resistance values. When and if I have a short circuit event, the circuit goes outside of the path, the normal path. And in most cases, it'll shorten that circuit because I take the load out of the picture. So my resistance value, when I take out the load, which was the bulk of the resistance in the circuit, I go outside of that normal path. Now I have less resistance, and when I have less resistance, I will have much more current. So short circuit currents are many, many magnitudes greater than your normal load currents, and many, many levels greater than normal overload currents. So if I have a motor, for example, if I have a treadmill and I jump on that treadmill, I'm going to cause that motor to work for a short period, well, maybe for a long period of time, you never know. But I'm going to cause that motor to do some work. It's going to draw more current, but all of that current stays in the normal path. When current goes outside of the path, that is what we call a short circuit or a faulted condition, and that's when the currents can get much, much greater than any normal overload in a circuit or any normal currents. Now, the one-line diagram, remember I told you the one-line diagram is a critical piece of this picture. And by looking at this one-line diagram, when I understand where my utility is and where my loads are, and I understand what size conductors and all of that good stuff, I can get a general overview of my power distribution system. So the single line diagram is critical, and it has to be up to date. I did a 1 hour session, and it's on my YouTube channel. I went live with it. That was the first time I went live. But I have a 1 hour session on that talks about the importance of the single line diagram and all of the code references from a 70 National Electrical Code, 70B from maintenance, and 70E from the electrical safe work practices on how important the one line and single line diagram is. But if I just review this overview, I know that the fault currents will be less the further I get away from the utility or my service entrance equipment, as long as I don't have big generation, downstream. Just in normal practice, my fault currents will be less the further I get away from the service entrance equipment. It'll depend upon the lengths of the conductors and et cetera. So from an electrical safety perspective, as I go closer to my utility, I know my fault currents are going higher. And we're going to talk about tomorrow, in tomorrow's sessions, the selective coordination. We'll talk about intentional delays and what overcurrent protective devices can and can't do and what they do. But in any case, suffice it to say, as I get closer to the source, my fault currents are going to go greater. So my sources of short circuit current are utilities, generators, motors, your induction and synchronous motors. Now, I could throw in other items like photovoltaic systems, wind. If I talk about wind, really, I'm talking about a generator, so to speak. Now, motors, if I have a motor on a variable frequency drive, if you want to split hairs with me. If I'm on a variable frequency drive, that VFD will limit the amount of fault current. It won't provide that contribution from motors. Cross the line starters is what we're talking about there, but just the motor in general. If there's a short circuit above upstream, I collapse the voltage on that motor. It becomes a generator. But obviously there are nuances there. But this is sort of, transformers aren't on this list. Whenever I talk to people, I'll say, give me some sources of fault current, and inevitably you have the hand go up and say transformers. Now we think about transformers, but as a utility service, but it's the utility on the primary of that utility transformer that's doing the work for you and generating that fault current. Reducers of fault current are your transformers, cables, fuses, circuit breakers, busway, panel board bus, reactors, arcing. All of these things act to impede the flow of current, but we don't normally model all of these in a power distribution system. We look for the big hitters. Transformers. There's a lot of impedance in transformers. You want to knock fault current down, throw a transformer at it. Cables will reduce fault current. Fuses have an impedance. Circuit breakers have an impedance. Panel board, the bus inside of a panel board, they have an impedance, but is insignificant in comparison with cables and transformers and reactors and busway and things of that nature. We don't model the impedance of a fuse or a circuit breaker. We don't model the impedance of a panel board. Those resistance and impedance values are very small and insignificant in the overall picture of our calculations. We will model arcing, and we do that in the form of IEEE 1584 arcing fault calculations that we do to determine incident energy. Reactors, that'll add a lot of impedance. So these are all things that reduce fault currents. Now, if I put two of these in parallel, I can increase fault current. So you take transformers, utilities on secondary networks, they'll have a network of transformers, and they're all in parallel. And the more I put in parallel, the higher my fault current contribution will be. So I can do the same thing with cables and conductors, like we said in that quiz question. I take two conductors, put them in parallel. I decrease the impedance by 2, and that means I've increased my fault current. So some of these can increase fault current depending upon their application. But in general, they are an impedance. So let's talk about why we calculate short circuit currents. We have to worry about interrupting ratings of overcurrent protective devices. We need to worry about the short circuit current ratings of equipment. We'll need the short circuit study is actually it's like the most fundamental study that we do on any power distribution system. You have to do a short circuit study. For a lot of different reasons. If I'm going to do an incident energy analysis, I'm really going to need to know my fault currents. If I'm going to do selective coordination, I need to know my fault currents. And the incident energy we're going to be talking about on Friday. Selective coordination is tomorrow. We're going to dig into those details to help you understand the whys. And then there are NEC requirements, National Electrical Code requirements, that tell us we need to mark available fault current. And if you've watched the 2017 National Electrical Code, and especially the 2020 National Electrical Code, there are more and more areas where you need to field mark available short circuit current. Now remember, exceeding interrupting ratings. If you misapply a product, I don't care what it is, and you misapply it from a voltage perspective, from a current rating perspective, an interrupting rating perspective, I can't tell you what the outcome is going to be. I can tell you that it probably is not going to be favorable. So calculating short circuit currents, we need to understand and compare that with our interrupting ratings. An interrupting rating is the ability of the overcurrent protective device to stop the flow of current. A fuse and a circuit breaker do not have a short circuit current rating. They have an interrupting rating because they stop the flow of current. And there's a requirement in 110.9 of the National Electrical Code that tells you that it has to have the ability to stop what you're throwing at it. So we have to do that analysis. In Article 100, they give us a definition of what an interrupting rating is. And again, it'll be dependent upon the voltage as well. So you'll see equipment that'll say circuit breakers will have an interrupting rating that will be one value at 240 volt, a different value at 600 volts. And it may be different versus AC versus DC. So it's important to understand the interrupting ratings and what the capabilities, and ensure you are protecting that equipment, or you are providing and applying that equipment within its rating. So I'm going to show two videos here. One video is a fuse that has had its interrupting rating exceeded, 10,000 amp interrupting base fuse that has, I believe, 50,000 amps of fault current that it's trying to stop. And then I'm going to show a circuit breaker that has the same amount of current, but it's got a 5,000 amp interrupting rating. And we're going to show what happens to these two solutions when you misapply them in the field. So let's check these out. Please remember to mute your phones. So that's a fuse exceeding its interrupting rating, being severely misapplied. That is a circuit breaker exceeding its interrupting rating. And what Dan Neeser would call that is an unintended rapid disassembly in the field. You let the smoke out. You don't want to let the smoke out. It costs us a lot of money to put smoke in. You don't want to let the smoke out. Exceeding the interrupting ratings is ungood. It will cause a catastrophic failure. It can cause an arc flash event. And we rely on these products and these solutions to reduce incident energy, not contribute to it. Now, short circuit current ratings of electrical equipment can cause serious worker injury and equipment damage in a facility. And the next video I'm going to show you is another piece of equipment that has had its short circuit current rating exceeded.
3, 2, 1, 0.
Now, the important thing about this video is the short circuit problem didn't occur inside that equipment. It actually occurred downstream of that equipment.
3, 2, 1.
So to give you an example on this in this video, you know, everything inside of this equipment is perfectly fine. At the end of this conductor down here, we short circuited it. You can't really see it on this video screen, but we created a voltage short circuit event downstream of this equipment, and the current flows through this conductor. This high short circuit current flows through this conductor, through all of the current carrying components in that equipment, and feeds the short circuit. Now, electrons are party animals, all right? They're very social people. When there's a party going on, like a short circuit event, they all want to get there, and they want to get there as fast as they can, and they're going to rush through anything that you put in its way to carry that current normally. In this case, it's a starter. There's a circuit breaker in there. There's probably a terminal block in there. And what happens with short circuit current, remember that waveform that we showed in earlier, that peak current? I told you the magnetic forces that the peak current places on the system. This is what it can do when you misapply a solution. In this case, this equipment was misapplied. The short circuit current rating. All right, we need a mute. Please mute your phone. Hold on, let me. I'm going to stop sharing, and I'm going to mute. Go participant, mute all. I have muted all. Please mute your phone. I hear talking in the background, and I cannot mute it. Please mute your phone. I can't tell who it is. And I have gone to participant and mute all. There we go. Thank you. Thank you. Share content. And we're back to our normally scheduled program. Thank you very much. For those on YouTube, you now know what you're missing. All right, so that's basically what the short circuit current rating is it lets the current pass through it. So I'm going to talk a little bit about short circuit current rating because it is different than the interrupting rating. 110.10 of the National Electrical Code tells us that a short circuit current rating must be greater than the available short circuit current. And really, it's the fault current that's going to be passing through that equipment. Equipment doesn't stop the flow. It's the components inside that stop the flow of current. But so you've got to understand what a short circuit current rating is. And I have a sort of an example to help us understand that. I always use a weightlifter example. So if I think about who the players are from a weightlifting perspective, you've got the individual who's laying on the bench, who is the distribution equipment. So the weightlifter himself is the distribution equipment. The weights that he's lifting are the magnetic forces being placed on that equipment. So the fault current flowing through that equipment that we saw achieve a rapid disassembly in the field, those are the fault current magnetic forces being placed on that equipment. And the gentleman who's standing behind this weightlifter is the overcurrent protective device. He's the spotter. That spotter's job is to make sure that the weightlifter doesn't hurt himself and go to the hospital. The spotter's job is the overcurrent device in this picture, and the overcurrent device's job is to make sure that the equipment is protected. So what the spotter does, if the weight is too much to handle, the spotter's going to take the weight off of the system, off of the weightlifter. That's what a current limiting fuse does, or a current limiting overcurrent protective device does. So we talked about this in the beginning of this course. This waveform is 1, 2, 3, 4, 5, 6 cycles of current without an overcurrent protective device in the picture. I could have remember what a cycle is. This is a 60 hertz system. So 1 over 60 is your one cycle of current. That's 0.016 or 0.0167 seconds. So every cycle is 0.016 seconds. So this is 1, 2, 3, 4, 5, 6 cycles. We're talking about 0.1 seconds. So if you want to relate that to a clearing times on overcurrent devices, this is 0.1 seconds worth of fault current flowing. When I have a current limiting device in the picture, I'm going to limit. Remember, when we talked about current limitation, we limit the peak. We limit this peak to a new value of peak, which is down here. I've reduced the magnetic forces. We've also reduced the time that the current is permitted to flow. So instead of seeing all 6 cycles, the equipment that's being protected will only see that peak let through for less than 1/4 cycle, which is less than 0.0. Remember, one cycle is 0.016. 0.008 is a half a cycle. 0.004 is a quarter cycle. So I am faster than a blink of an eye. The overcurrent device is going to open if it's opening less than a quarter cycle. And that relates to this, which we looked at earlier, and the answer to that up, over, and down method, the let through perspective. This tool is what the industry uses to determine how much current is really being let through by the overcurrent device. Now, the best way to understand the magnitude of what we're seeing here is to watch a video. So I'm going to set you up with, again, your spotter's function is current limitation. We have an example of 90 foot of 2-aught conductor. I'm going to let 1 cycle of fault current flow. I'm going to let 26,000 amps of 1 cycle. If you're familiar with a 2-aught conductor, it's pretty stiff. And we're going to watch what happens to this conductor when 1 cycle of fault current is permitted to flow. It's a very violent. You can see the magnetic forces engaged with that conductor. And you think about, I use this video to help people understand the importance of torque, that people understand the importance of using the right bolts to mount pieces of equipment on the wall. I mean, these are the magnetic forces that a power distribution system sees when fault current flows. And that's one cycle of fault current. Now the peak current, remember this is the peak for one cycle. So one cycle of flowed, there's no current limiting device in the picture. My peak current was 48,100 amps. The I squared T, which is the amount of energy, is 15.7 million amp squared seconds. There's a lot of heat and there's a lot of peak currents, a lot of magnetic forces that you visibly saw. So now to help you understand the power and value of current limitation, in this same scenario, everything else being equal, we put a 200 amp class RK1 fuse at the head of this circuit, and we did the exact same analysis or test. Let's take a look at the results. You're going to want to watch right here. Okay, that was the exact same analysis. Let's do this again. Because I think it's important to see this one more time. Now, what did that translate into? That translated into reducing that 48,000 kiloamp peak to 10,000 amps. And the let through energy, which was the I squared T, that was 127, it was I think it was like a 15.7 million, is now 127,500 amp squared second. So I reduced my peak current, and I reduced my let through peak current and my I squared T energy considerably. That translates into less force on my power distribution system, and it translates into lower incident energy as well. And that's the power of current limitation in a circuit. Now, if you don't have that, if you let all of that current through, you're bound to damage your pieces of your equipment because it's going to be misapplied. If you can't lift that much weight, don't try it by yourself. Make sure you have the right spotter if you're going to be placed into that scenario. My question always is, who is your spotter? If you have a piece of equipment that's rated 100,000 amps or 200,000 amp short circuit current rating, do you have that guy protecting that equipment? Or did this guy say, hey, you know what? Hey, Lou Ferrigno, he's over in the lavatory. I'm going to help you out with this, right? If you have the wrong overcurrent protective device in the picture that's not identified correctly, you have to ask yourself, who's your spotter? Okay, that was 35,000 amps of fault current through a 5,000 amp short circuit current rated piece of equipment. That door flew about 25 feet in the lab. It was a severely misapplied solution in the field. And you'll notice down at the bottom of that where the wires exit, that's where we terminated. So the fault wasn't to start in the equipment. The fault was short circuit downstream of that equipment, but the components inside just couldn't stay together because we didn't have the right application. Now this one is 5,000 amp short circuit current rating and 35,000 amps available fault current. That's a plastic enclosure. You can see the short on coming out of the right hand side of that equipment where we created the short circuit. That's a catastrophic failure that you don't want to have in a facility. If you misapply a product, you can get an unintended rapid disassembly in the field. So 110.10, and I always say short circuit current rating of equipment it's important to understand the mix, that equipment, you first have to understand what the rating is. You next have to understand what the maximum short circuit current is, and then you have to compare the two and make sure that your rating is greater than the available fault current. The National Electrical Code has various areas where you have to mark the short circuit current rating on equipment. These are all the sections in the NEC where you have a requirement that the short circuit current rating on equipment is required in the field. Pretty much every one of these are covered by the standard if you buy a listed product. With exception on transfer switches, it can be a little bit of a challenge because transfer switches, the short circuit current rating of that equipment will be based and dependent upon what's installed upstream. And what we do on a transfer switch is give you the recipe, so to speak, on how to determine the short circuit current rating or the withstand close-on rating, and then you have to do the comparison. So it'll be dependent upon what's installed. Now, the other thing that we require is the available short circuit current, and there are requirements in the 17 that have been expanded in the 2020 code to require a field marking of available fault current on equipment. We've had it in service entrance equipment in 110.24 for a while. That's expanded to other equipment. 408.6, that is the new boy on the block is right here on 408.6. That's all panel boards, switchboards, and switchgear now have to be field marked in the 2020 National Electrical Code with the available short circuit current. Very important parameter to know. And then this is your ratings. These are the 110.10. Since it's in Chapter 1, it applies generally. Any equipment, you have to do a comparison of the rating with the available fault current. So these are the reasons why we are calculating fault currents. Arc flash hazard warning in 110.16. Look what's on the list here. We have available fault current. Look at this. You need to know the available fault current if you choose option 1 in 110.16. If you chose the exception, which is using the IEEE 1584 or NFPA 70E calculation and labeling method, you won't see fault current on there, but you're going to need fault current to calculate incident energy, which is the tool for that is IEEE 1584. So 110.24 requires a field marking on service entrance. Now we have the Bussmann FC Squared app. That is a free download that can help in facilitating that labeling. For the engineers on the phone, there's an opportunity to provide a service to the industry to make sure that we meet these requirements of marking of available fault current. We've got to do this study. Any modifications that we make to a system, you add motors. We know motors contribute fault current. If you subtract motors, all of those things will impact available fault currents. 230.82, equipment connected to the supply side. These are your cable limiters, your meter sockets, and whatnot. There was a recent change in the National Electrical Code that requires us to look at power distribution blocks to make sure they have the right ratings and other types of connectors. And in this last code cycle, in the 2020 cycle, we were asked to do some testing by some code making panel members, and we did some testing. And here's the video that we provided to the panel to help them understand what are the capabilities of these types of split bulb solutions. So that was a 10,000 amp bulb and held together. That was 22,000 amps. It didn't quite hold it together. This is 3 cycles of current, by the way. 3 cycles passing through this termination. And you always do slow motion. When you have a good one, you got to do slow motion. So that's that what you see there is it came out from under the lug. And the question at the code panel was, there was a requirement around power distribution blocks. We didn't have a requirement on these other methods. And would they hold together? This is a different type of connector. It held its own in that test. Now you see all that smoke, you wonder if that conductor is damaged or that termination should probably be looked at. So that's another reason why is not only the electrical distribution equipment, but every little part that has to carry the fault current to its destiny, which is the fault, needs to be rated correctly and applied correctly. Another area is selective coordination, and which is a detail of tomorrow's presentation. Okay, so those are all the reasons why we need to do this. And as we walk into understanding the power distribution system, the first thing I want to cover quickly is what are we asking in this power distribution of the system to do in normal conditions? Because remember, this is the dam and everything doing things normally. So here's your typical power. I mean, it's the one I drew. So forgive me for my artistic inabilities, but that's an example, small one-line diagram. All of the equipment in this picture is rated to handle things normally if you've sized them correctly. I have the transformer, which I can calculate full load amps on the secondary, and I can compare that with my load calculation on what I'm expecting to deliver to my system. And I want to make sure that I have the right size transformer to supply the loads. I want to make sure that all of my conductors have the right ampacity. So I'll use the ampacity tables from the National Electrical Code 310.15b16 or 310.16, depending upon which net version of the NEC that you're on. I want to make sure that all of my circuit breakers have a handle rating that can protect the conductors and not trip based on either normal flow of current or inrush current of that transformer. They're going to be sized for normal operation. My fuses will have to be sized for normal operation if I have a fused system as well. My assemblies, all of my assemblies will have a standard voltage rating. They'll have an ampere rating. I'll know what the bus can handle. They'll have environmental ratings. I wouldn't take an enclosure that's designed for installation indoors and put it outside and expect great results. All of these things are important for normal everyday usage. I have motors, they have specific horsepower, they have torque relationships, they'll know how much work they can do. We size everything for normal operation, and we're following the National Electrical Code for installation and manufacturer's instructions for the installation of this equipment so that it operates and functions as we expect it to do. So now, all of this has to work correctly, but what happens in abnormal conditions? So this is when we subject the power distribution system to an abnormal event. That would be an example of that is a fault that occurs downstream somewhere in the system. I have a short circuit event, which could be an arcing fault. It could be a dead short, depending upon the actual event itself, will dictate the level of current that the power distribution will see. The things that we think about when we have to consider this type of an event, I'm still going to look at my transformers, but I'm not necessarily worried about will they provide the full load amps to the load. I'm more worried about what the impedance of that transformer is and what is it going to do to reduce the fault current that's going to be delivered. How is it going to react during this fault condition? When I think about conductors, I'm thinking about the impedance of that conductor, because remember, I'm creating a circuit. I have a source, a voltage source, I have a short, and I have conductors and anything that's going to deliver power. I'm not looking at the ampacity tables in the National Electrical Code. I'm back in Chapter 9 looking at Table 9 for what the real and reactive components are of the impedance of a conductor and the length of that conductor. My circuit breakers, I'm not worried about what the handle rating is, if it's a 30 amp, 100 amp, and is it going to let these currents flow, the normal currents flow. I'm worried about the interrupting capabilities of this device. And you'll see on this, from an example, and I mentioned it earlier, we have voltage considerations. So I know that this breaker can interrupt 65,000 amps at 240 volts. But it's a 600 volt rated piece of equipment device, but it'll only interrupt 18,000 amps at 600 volts. If I read the wrong number and I applied this breaker with 40 or 50,000 amps available, and I applied this breaker in a 600 volt application because I didn't pay attention to the details that 65K is only at 240, I'm going to misapply that product. And we saw what happens if I misapply a product. Fuses. I have a similar situation. Now I'll point out on this one that although from a UL perspective, I have a 300,000 amp interrupting rating AC, I have a 100,000 amp interrupting rating on the DC side. So not only does voltage make a difference, but DC versus AC makes a difference as well. So we have to understand the capabilities of each of our devices when we apply them. Now, electrical distribution equipment is going to have a short circuit current rating. And this label is from a switchboard installation. And you'll see they're not very clear. As you don't see a label on a switchboard or a panel board that says, hey, this is 65K or this is 22K. The assembly itself determines, and how it's installed and what you put inside will determine the short circuit current rating of that equipment. And honestly, as a manufacturer, when I ship this equipment, I don't know what the short circuit current rating is going to be until you put stuff in it, right? So if I for the most part, on the large stuff, we ship this and it's engineered to order, but you have a panel board where you're putting in circuit breakers on the fly in the field. What you put in that equipment will determine the capabilities of that equipment. It's an important detail. Motors. Motors, I'm not worried about full load amps anymore. I'm worried about locked rotor amps. I'm worried about how much fault contribution is going to come from that motor to feed the fault. And when I have that fault, all of this stuff works together, and I have to understand the flow of currents in the power distribution system to understand the proper ratings and performance of all of my overcurrent devices. When I have motors and I consider all of the contributors to a fault, I'll know that all of this equipment is going to carry fault current, but some equipment will carry more fault current than others. So if I look at this bus from the motor and this portion of the circuit and this portion of the circuit, the only contribution to the fault in this other area of the power distribution system are the motors. So the fault current that flows through bus 17 and flows up through this 75 kVA transformer to bus 3 is going to be much less than what's delivered actually to the fault through that 225 kVA transformer, because the only portion of the only fault current that's being that bus 17 will see is the download motor contribution, which is going to be very small as compared to what's coming from the utility. So knowing the flow of fault current in the power distribution system is an important part of this recipe, and as we do an analysis of the distribution system, if I'm worried about incident energy and arc flash reduction, things of that nature, understanding what overcurrent devices see what current is important. So without the motor contribution, bus 17 doesn't see any fault for a fault over on the secondary of that 225 kVA transformer. I won't get any I won't get any contribution from lights. I won't get any contribution from a heater. That's a heater element. If it's not a rotating piece of equipment, I'm not going to get fault contribution. It won't see, other than a voltage drop because of the short circuit, all of the contribution is going to be coming from the upstream device, upstream utility in this case. So understanding the flow of current is important for a couple reasons. And I'll help you understand one of those. This principle is important to understand series ratings. It's important to understand the 240-87 arc flash reduction requirements, the 240-67 arc flash reduction requirements, which we're going to talk about on Friday, and other types of analysis. But when I have no motors in the circuit, the main overcurrent device in this panel board and that feeder or branch device are both going to see the same current. The moment I introduce motors downstream, now they will contribute fault current. And now the main overcurrent device in this panel board will see less current than that feeder breaker because of that downstream motor contribution. And I need to understand that for series rating capabilities, selective coordination, and incident energy, as I said before. So from a series rating perspective, if you're not familiar with that, the reason we would use series ratings is always, I'm going to reduce the cost of the installation. I'm going to install a 65K breaker on my main, and I'm going to install 10,000 amp interrupting breakers on my feeders or branch circuits. Now, in that case, the 65K and 10K breaker will both open together to interrupt the fault and do it safely. And they're tested that way. So In a fully rated system, everything in this case would be rated 65K. I'm seeing 31,400 amps. But when I do a series rated system, I would say I'm going to put 10,000 amp interrupting rating devices downstream with a 65K rated device upstream, and they will both work together to interrupt that 31,400 amps safely, up to 65,000 amps actually safely. Now, 24086 in the code talks about series ratings, and it says when you have motor contribution, you can't exceed 1% of the interrupting rating of the lower rated circuit breaker. And I'll tell you, this is a very commonly missed scenario in the power distribution system application. Motor full load currents can't exceed 1%. What that means is I add up all of those motors downstream, and if their full load amps exceeds 10% of, if it's a 10,000 amp breaker, 10% of, excuse me, if I have a thousand, say, what was it, a 10,000 amp circuit breaker, and I can't exceed 10% of that of that 10,000 amp interrupting rating from a motor contribution perspective. So it doesn't take much to get me into an area where series ratings can't be used. You have down heavy industrials. I had one gentleman who I did an educational program like this. I explained this to him, and he says he thinks he has a problem. He engineers and put out what do you call it, car washing stations. And my first impression was, you don't have to worry about it. You know, it's a light commercial. And he goes, oh no, car washing stations are heavily motor intensive, and he series rates all of his equipment, which is ungood because he has a lot of downstream motor contribution. That's something that's often missed. All right, so in calculating short circuit currents, these are sort of what we calculate. Three-phase bolted faults, line-to-line-to-line faults, line-to-line, line-to-ground faults. We will calculate various types of scenarios. We typically want to migrate to the one that gives us the highest, because we're worried about interrupting ratings and short circuit current ratings. So the short circuit current rating, the three-phase bolted fault is typically your highest fault current that you'll see in a power distribution system. You can have line to ground short circuits that are higher, about up to 125% of the three-phase value. That's typically if you have when you're close to a transformer, and you'll definitely see that if you're on a single-phase system, secondary of a transformer, like say a utility transformer, you'll see the line to ground fault currents higher. We'll calculate the symmetrical and asymmetrical. Whenever we do an evaluation and compare equipment, we'll always compare on the symmetrical. We'll calculate the symmetrical, and I'll tell you, when you have to worry about the asymmetrical is when you have a specific X to R ratio that's greater than a certain number, because when we test overcurrent protective devices, this is a symmetrical fault current. Symmetrical fault currents have the first half cycle equal to the second half cycle. We don't test our interrupting ratings and whatnot on a symmetrical fault current, but we'll base the labeling on the symmetrical value. We will test with a specific X to R ratio, which will give us what we call a DC offset. Because in normal systems, this is what your fault current will look like. That first half cycle will be offset, and it'll be much higher than the rest, and that's the hardest portion of a fault to interrupt, is that first half cycle. What gives you that offset is what we call the X to R ratio, and that is your inductance to resistance, and that is based upon all of the different components you have in a power system. So the X to R ratio, typical ratios are from 5 to 6 or to 1, lower, much greater than 10 to 1. Right. So the more inductive circuits are more difficult to interrupt and stop the flow of current, and I'll help you understand why that is. This is an example of a resistive circuit. Your voltage and your current are right on top of each other. They both cross zero at the same time. They both peak at the same time. The moment I start adding inductance, now I'm getting an offset where my voltage is peaked when my current is crossing 0 in this case. My current has peaked. I have the most current when my voltage is crossing 0. So if my current has peaked to its highest value from a sine wave perspective and my voltage is 0, you can tell that would be more difficult to interrupt because my voltage is 0 and I'm trying to stop, but I have a lot of current flowing. My capacitive circuit has a little bit different. My capacitive circuit, I have my voltage at my peak, but my current is 0. So I can stop that flow of current quite easily at that point. So a system is normally not all capacitive. It's not all inductive. There is resistance in the picture. Now, when we talk about X to R ratios, it's really important to familiarize yourself with what I call the power triangle, what many people call, the industry calls the power triangle. You know, we can relate all of this to trigonometry. I have reactance on one side of the axis, I have resistance across the bottom, and I have an effective Z. This can be represented, this can be VARs over here on the right, this can be watts across the bottom, and this is VA on the hypotenuse. We use this power triangle for a lot of different applications. The angle is your power factor. So cosine theta is your power factor. The X to R ratio is the ratio of X to R. And if I know my power factor, I can calculate my X to R ratio by giving my inverse tan theta, or tan theta, the tangent of theta. Again, it goes back to trigonometry. These are all the equations. These are some of the equations that you would use. And but the important part of this is to just simply understand that the power system is going to be out of phase with each other. Voltage and current are going to be out of phase with each other, and that will depend upon the X to R, how much X you have, how much impedance you have in the system for the resistance. And if you just mapped out the power factor versus the angle versus the X to R numbers, you'll see how as my power factor decreases, so lower power factors will give me a higher X to R ratio because I have more X in the picture. And the key number for any overcurrent protected device is right here around 15% power factor. That's what we test these devices with in the lab. And you're down around a 6.5 X to R ratio. And this basically, I've got a few slides. I'm just going to pass through them really quick. It basically maps out voltage and current. That's at 90% power factor, 80% power factor, 70%. You can see the current is getting more and more out of phase until it reaches that magic point where it's completely out of phase with each other. So the X to R in the overcurrent protected device, remember that the overcurrent protected device can interrupt, and it's tested to interrupt at a specific or anticipated worst case X to R ratio. And beyond that, you may have to apply derating factors. And in this case, the 6.6 is the X to R ratio is 6.6. That's the number you're looking for, or less. If it's greater than 6.6, that means you have a lot of inductance that you're trying to interrupt. You may have to derate the interrupting rating of that overcurrent protected device. So X to R ratio is an important area to focus on. And it's rarely looked at, but if you look at any of the outputs, SKM, EDSA, Easy Power, they'll give you a short circuit study and they'll tell you what the X to R ratios are at the very buses, multiple buses that you're looking at in the system. So that's an important piece of the pie that you need to think about, and it's all dependent upon impedance. So if you think about the process, secure and accurate one-line diagram. You have to create the impedance diagram, use Ohm's law and Thevenin equivalent, and then you calculate your short circuit at every bus. And then that's what's going on behind the scenes. The power triangle is a very powerful tool to understand. I could probably do a separate session just on the power triangle and all the different equations, because it's back to trigonometry. It's a fundamental tool. It can help you understand the power distribution system. It'll help you understand the proper ratings of your overcurrent protected devices and application of the devices. We use this triangle for power, apparent power, watts. I already talked about that, and impedance. And again, a whole nother area that I will more often get into. But every component in a power distribution system can be broken down into either just a resistance, just a reactance, or a combination of real and reactive impedances. Those are all critical parts of the pie that help us understand the flow of currents in the power distribution system and the ratings of equipment. Let's talk about some contributors: utilities, generators, and motors. Fault current contributor, utility. Utilities will provide you the available short circuit current, but unfortunately, sometimes they will provide, they'll sometimes provide you with, you call it available short circuit. They'll provide you with MVA short circuit. They'll give you different values, and you've got to learn how to deal with that. But this is an example from Florida Power and Light. They'll, upon request, they will inform the customer of available short circuit currents. There's an example of Alabama Power. They have resources online that you can download for all of the different size services and their pad mount transformers. My personal opinion is that you should contact the utility, and what you'll find is when you find the right individual at every one of the utilities where you do your work, you'll have one resource that you'll get to know them on a first name basis, because you'll be reaching out to them quite often to understand what the available fault current is from the utility. I know sometimes it can be a little bit more difficult with some utilities than others, depending upon the size of the utility and the resources that they have available, but for the most part, a really good resource for you. They'll give you sometimes the short circuit current available. They'll get you the MVA or KVA short circuit. They'll always give you an X to R ratio as well. And now you understand what the X to R ratio is. It's the source looking at the utility. It's how much inductive versus resistance in their entire distribution system. And you're going to do the same thing, or SKM or EDSA or Easy Power will do the same thing when you model your power system in their tools. This is the screenshot of the entry points, the data that we would put in. You'll notice that you have the fault contribution in this area here. In this case, it's MVA, but you can pull that down and you can show short circuit current. There's your X to R and any tolerances. Infinite bus, you can select an infinite bus. I'll give you an example of what that means to help you understand that. So what is an infinite bus? I've got a separate YouTube video on this. I'm going to walk through these slides. If you really want to understand it, I would suggest you watch that YouTube video. The infinite bus gives you the most current that could possibly be seen on the secondary lugs of any transformer. It assumes that the utility is right outside your door and right next to that transformer. And here's how we come up with it. For just like in any circuit, if you're going to calculate short circuit currents, you're going to create a little diagram. It gets back to Ohm's law. You're going to say, okay, I have a utility equivalent impedance. You're going to convert that to an impedance, whatever. If they give you available short circuit current and an X to R ratio, you're going to convert that information into a source utility equivalent impedance. You have since the transformer percent impedance is in per unit, you may not understand what per unit is. I'll have another video on that as well at some point. 5.75 divided by 100 is 0.0575 per unit. So I will calculate a utility per unit value and a transformer per unit value. Add those two. V is equal to IR. Voltage over impedance gives me my short circuit, and then I will convert that to an actual short circuit. There's the equation to get the transformer percent impedance into per unit. You just divide it by 100, piece of cake. And then here's my utility equation. So to convert available short circuit current that the utility gives you, in this case 20,000 amps, to convert that to a per unit impedance, you'll notice that 20,000 amps is in the denominator. I have to divide KVA base, the KVA of this transformer, divided by the short circuit current, divided by square root of 3, divided by 4160 as the KV base. And what that gives us is I can create a table to show that varying the utility fault current, as the fault current increases, as it's in the denominator, as my fault current increases, my utility impedance will approach zero. As the denominator approaches infinity, my impedance approaches 0, hence an infinite bus. So an infinite amount of fault current on the primary side of that transformer will give me 0 impedance from the source. So if I looked at my little diagram again, my utility impedance, because of that fact, my utility impedance goes away, and now I'm just left with a transformer. And to calculate my short circuit is my impedance, is my full load amps over my impedance. Now, I've had a lot of people say, well, varying the fault current on the primary of a transformer will significantly impact the fault current on the secondary of the transformer, which is untrue, if that's a word. The impedance of that transformer is so significant that the variance on the secondary of the transformer varies not as much as you would think. So if I go from infinity, if I assume an infinite bus, I have 31,378 amps on the secondary of this transformer. If I drop infinity down to 20,000 amps, I only go to 26,000 amps. That's not much of a difference. From infinity to 20,000 amps of available fault current on the primary of a transformer, I go from 31,000 to 26,000. Not significant whatsoever. If I assumed 50,000 amps of fault current on the primary of a 1500 kVA transformer with a 480 volt secondary and a 5.75% impedance, my fault current infinite bus would be, or with 50,000 amps of primary, would be 29,000. But if my utility said, hey, look, sorry about that, Tom, I increased your fault current, not 50,000, but I doubled it to 100,000, I've only increased my secondary available fault current by 3%. I went from 29,259 to 30,281, which is not very much at all. But we should never size equipment so with interrupting ratings or short circuit current ratings that close to the actual available fault current, because any changes could cause me a problem. So, and this is just another way to look at it. I looked at the percent difference between infinite bus. If I go for infinite bus and I lower it by 8%, my percent change in utility on the secondary, if I change my utility from infinite bus to, I lower it 60%, I only incurred an 8% drop in fault current on the secondary of the transformer. And the reason is because of the significant impedance of that transformer as regard to the utility equivalent impedance. Now, they would have to change your transformer to significantly impact the secondary system in your power distribution system. But if you're in a downtown network like downtown New York, Houston, Dallas, Pittsburgh, Pennsylvania, any of these downtown networks will use what we call secondary networks. And this is what they do in a secondary network. You're given a service, but they will parallel transformers. And what do we learn about paralleling? That reduces the source impedance, which will significantly increase the fault current to your facility. So they'll typically, and most of these secondary networks are going to be fused anyway, so you'll have 200,000 amp interrupting rating or 200,000 amp short circuit current ratings, and you won't normally have that problem. That's typically a fused application anyway. But in any case, those are typically going to be the areas where we're going to have high fault currents, and they can be very complicated networks. That is when you're going to really check with your utilities. The utility available fault current is required. All your utility, I would highly say you need to establish that relationship. Generators. Let's take a look at the impedance of generators. Now, generators, are usually turned by a prime mover like steam or a diesel or some sort of engine, and they will contribute fault current. Now, a generator could be wind, which may turn on and off depending upon how much wind you got blowing out there. But in any case, for the most part, generators are going to be a constant source of power to the system. Utilities don't just shut their generators off at night, right? So those things are going to be pumping all the time, and it's just a significant amount of fault current that can be there for a significant amount of time if it's persistent. Because the generator is driven by a separate prime mover, the available fault current will not decay over time. Unlike a motor, if I'm on a motor and my motor is turning something and I collapse the voltage to the motor, that motor will decay in its contribution of fault current because whatever I'm driving is going to slow it down. If I'm driving a conveyor belt, it'll slow or faster than if I'm doing a fan that can free float. So generators, though, are being driven by a prime mover. They will be there. This is the typical circuit. This this impedance is what is required in the National Electrical Code to be labeled, and that's what's going to be important in our calculations. Section 445.11 of the National Electrical Code tells us that we have to put on the nameplate information, and we have to put the subtransient, transient, synchronous, and zero sequence reactances. We have to have the power rating category, etc. But these impedance values are what's important to the power systems engineer to model how much fault current you're going to receive. Now, here's what the subtransient reactance gives you. It determines the maximum instantaneous. That's what we're worried about, is that first half cycle. And subtransient reactance is how we model that generator for the first 6 cycles. So, and it's going to be a lower value of reactance than anything else. As time persists, the reactance will change in that generator from a magnetic perspective, all that good stuff. The transient reactance gives us the response of that generator from 6 cycles to 5 seconds. And the synchronous reactance gives us after 5 seconds, so that's continuous. Zero sequence, that's your ground faults. Anytime you hear zero sequence, that means ground faults. Negative sequence, that's typically when you have an unbalance of some sort. We're not going to get into symmetrical components, but we could at a later date. So this is, again, these are just some slides that say the same thing that we just showed. So I'm just going to flip through these for sake of time. There's your transient reactance. There's your synchronous reactance. You can always, again, check this out on YouTube. You can pause it, go back through and take a look at some of these numbers. Most of these numbers came from IEEE references. That's sort of how a generator responds and reacts and contributes fault current to the system and the impedances that we use. Now let's talk about motors. Where do we find electric motors in a power distribution system? We find them all over the place, but we don't model every motor. I mean, there's a motor in the little heater that I might have underneath my desk. There's a motor in my refrigerator. There's a motor on a lot of different pieces of equipment in the power distribution system. And I don't model all of those. I model some of the big ones that we have in the system. What happens with a motor is the voltage will collapse, but that rotor will continue to turn. So I may not be driving the rotor anymore. The rotor is now driving whatever is driving that rotor. Like I say, it's a fan or a pump. That will continue to turn, and the motor becomes a generator. And the back EMF will now contribute fault current. The size of the motor matters. And that's why on a lot of the less than 50 horsepower, a lot of the real small ones, quarter horsepower, we don't even think about those. They're here today, gone tomorrow. I mean, they're gone really quick. But the larger motors will hang in there, and we'll model those in our systems analysis software. They'll have, again, the same thing, a subtransient reactance. That's the number that we look for when we model for short circuit currents, because I'm worried about that first half cycle. Can't stress that enough that is the most hardest portion of the wave that I have to interrupt. You'll have a subtransient reactance. You'll have a transient reactance. It's just the same data we just saw in generators, because why? They're 2 rotating pieces of equipment. They're very similar to each other. And you'll have a synchronous reactance if your motor hangs in there that long, right? So we include connected motors. If they're less than 50 horsepower, we'll use a 1.67 multiplying factor on the subtransient impedances. If they're available, we can estimate some numbers, use IEEE rules of thumb, and we can estimate, and we can ignore, we can group motors. If I have 50 horsepower motors, I can just group them all together, add up the horsepower, and use a like 0.2 per unit impedance for that whole group. And this is a table out of some IEEE information, again, IEEE standards and documents that talk about this. In fact, I might do a little session just on my library and things that you should have in your library from an engineering perspective and from the contractor perspective. If you're into a design build type of thing, you want to learn more about engineering. This is your interrupting rating, is your contact parting duties for high voltage above 1 kV circuit breakers. obtained from the motor manufacturers that subtransient reactance, or you can use, again, a rule of thumb. If you want to estimate it, that's included in the bottom of this table. Estimate the first cycle network to be 0.2 based on motor ratings, 0.5. So they'll give you some examples and some ballpark figures. This is the screen out of SKM on where we enter this information. You'll note we enter the horsepower. You'll see in here they'll have a full load calculator. You have number of motors. You can actually link a library if you want to enter. You can get very specific, how many poles, all that good stuff. And this is your impedance. This is where you enter your subtransient reactance and your X to R values. Again, you can use rules of thumb from the IEEE Institute of Electrical and Electronic Engineers, or you can get it from the manufacturer of the motor if it's a big enough motor. All right, so that's how we model motors. They'll have an impedance. Transformers will have a similar. They're a working device, and contrary to what some people may think, transformers don't stop just because doing their job just because there's a fault downstream. They will continue to function just like they are supposed to, and they will transfer. They'll deliver that energy. They do add impedance, though. Transformers are all over the system. We don't model every transformer. In control power transformers, we typically don't model. When you get down to the secondary of some of these transformers based on infinite bus calculations, you'll know your fault current won't exceed a certain number. And I think I have some examples of that. So we basically model a transformer as an inductance. We assume resistance is negligible. It's primary. There is, transformers will have an X to R ratio, so there is an R value associated with it. In some cases, we'll enter that information. For the most part, if you're doing it by hand, you definitely don't. The systems analysis softwares will give you an assumed number, and there are some tables in IEEE and charts that we can use to determine the X to R ratio, so we can enter more accurate information, especially for those big transformers. Reactive components are typically only considered, again. The information you need to collect, like if you're going to do a systems analysis study on a power distribution system, you're going to do your walk down. You're going to walk down all of your conductors. You're going to walk down and look at all of your transformers and motors and record information. You need the kVA, primary and secondary voltage, and you need that percent impedance. Very important. Now, C5712.36 is our liquid immersed distribution substation transformers, and you'll notice, based on kVA rating, these are some rules of thumb. Again, they'll vary by manufacturer. This will tell you what your impedances are at various voltages, and you'll notice 750 to 4999. There's that 5.75 number that we all come to love and use for those 1500 kVA transformers and 1000 kVA transformers. Anything above 750, we're going to use a ballpark figure of 5.75. And there are tolerances, though, and this gets into that one question that we had in those in the quiz where we reduced it by 10%, and I'll show you where that comes from. It comes from the standards on how what governs the marking of these transformers. So C57.1201 covers the dry type transformers. Now here are the tolerances. So for impedance, the impedance of a 2-winding transformer no larger than 2.5%, with impedance voltage larger than 2.5%, will have a tolerance of plus or minus 7.5% of the specified value. A tolerance for those with impedance voltage of 2.5% or less shall have a tolerance of plus or minus 10%. Differences of impedances between, so that means that if I'm marking a transformer, if it meets these criteria, my marking can vary. I'm going to put 5.75, but if it's a 2-winding transformer and it's 5.75, so it's greater than 2.5, I can be plus or minus 10%. If I look at 9.2 of that standard, talks about impedance of transformers having 3 or more windings or zigzag windings, shall have a tolerance of plus or minus 10% of the specified value. So if I see a marking of 5.75% and I'm worried about interrupting ratings, I'm worried about a higher fault current, I'm going to lower my impedance of that transformer by 10%. And that way I know that based on how it's manufactured and based on the fact that the manufacturer knows that your tolerance is going to be plus or minus 10%, but I'm going to put 5.75 on there, that's not the actual, that it could be 10% less, it could be 10% more. If I'm doing an arc flash analysis, I'm worried about lower fault currents and higher fault currents, so I'll probably do a study where all my transformers have plus 10% impedance and all of my transformers have a minus 10% impedance. And my software will do an analysis in that regard to give me worst case scenario. Again, the impedance of an auto transformer shall have a tolerance of plus or minus 10%. So for those who did the calculation, and I've done the same thing, I'll just do 5.75 and get my ballpark figure. I shouldn't be designing my system to where that 10% makes a difference. But we all know that dollars and cents counts, and it drives us to do some crazy stuff. So tolerances for impedance shall be as follows. So this, again, these are just out of the standards. I even reference here UL 1561. They will reference, this is the percent impedance for, this tells us that 25 kVA or more shall have an impedance, and the marked value is acceptable if it is within a plus or minus 10%. Anything less than a 25 kVA will not have an impedance mark, or it's not required to have an impedance mark on the label. So there's just references to the standards. This is your impedance data for the three-phase transformer. Again, ranges. This is out of IEEE standard. So suffice it to say that a transformer is going to have, it'll be marked with an impedance, but that actual value can vary plus or minus a percentage based upon the standards, the size of transformer, and the transformer that you're dealing with. So here's an example of a label of a transformer. You'll see there's the impedance data, and that's going to be an important part of the picture. So what's the maximum amount of fault current possible on the secondary of a transformer? There's your iShorts, there's your calculation. You take the kVA times the square root of 3, divided by 3, divided by the secondary voltage in kV, because you have kVA up above. You have to have the kV down below, and then you divide that by the per unit impedance. In this case, it's 0.0506. Some people will just say put 5.06 on the bottom and multiply the numerator by 100. I just do the math outside of that and just put 0.0506 in the denominator. Now, it's either going to be 4,114 if I don't include the minus 10% on the 0.0506, or it's going to be 4,571 if I do include the 10% reduction in impedance. Okay, if you're doing calculation, now these may add up. Take that into consideration. These may add up with all the different transformers that you might have in a power distribution. And I do the same thing with this transformer. And again, it's just an exercise. So the most fault current you can expect at that location for a 1,000 kVA transformer, if you do the math, 21,000 amps. So if I buy 22,000 equipment, 22,000 amp short circuit current rating of equipment on the secondary, I'm fine. But if I did this in the as-built phase, and I bought 22K equipment, and if I did this in my design phase, and my as-built drawings show a different impedance, a very slightly different impedance, I could have an issue by exceeding the interrupting ratings or short circuit current ratings of that equipment, depending upon the length of that cable. 22K on that one. And so if I did all of the math on all of these, I have 21K, 22K, and 8K. So this really gives you a feeling that if I calculate infinite bus, that'll help me with confidence either in my design phase on what SCCR ratings and interrupting ratings I can put downstream and whatnot. Now, if I add fans to a transformer, this is another important little detail I'm going to cover really quickly. That, remember, I'm adding fans to get more kVA out of it. But the message that I'm trying to tell you here is that it doesn't impact the impedance. I can have an ambient air rated, an AAFA with fans added. I can have a future fans added, meaning they're not on there right now, but they can be added in the future. I can have oil or forced oil, or fans and forced oil. An example of this is this 3750/5000 kVA. This is an AAFA. I will have different full load amps based upon how much kVA I'm pushing into the system. or I'm adding to this load of this transformer, and I can work this transformer very hard, and you'll see that my kVA changes from 3750 to 5000. If I add fans, it goes up to 5000 capability. That means my full load amps will increase. My voltage stays the same on the secondary, but you'll notice that the impedance does not have two ratings because you can't change the physics of the construction of that transformer. If it has a 5.92% impedance, I don't care if you add fans or not, it will always have a 5.92% impedance. And you calculate the full load amps, or you calculate the available fault current on the secondary based upon the standard rating of that, which is the 3750, not the 5000. Important detail to not miss. Remember, adding the fans are there to work that thing hard and give you more kVA, but it doesn't change the physics and construction of that equipment. When I'm going to do my calculation, I'm going to take that full load amps, 4511, which is based upon the 3750 kVA. I'm going to divide that by the impedance, 0.0592. And what I didn't do it here, but you should have taken minus 10%. So I fell into my own little trap. But if I don't do the 10%, I'm at 76,200 amps. So that's sort of how you get to that end point when you have fans loaded up. And again, there's this is the entry of the information for transformer when in an SKM systems analysis software. I'm adding the kVA, I'm adding my voltages, and then I will add the transformer impedance. I'll have a %Z and an X to R. You can look at IEEE references, gives you the ballpark X to R ratios for transformers, and you can enter that information into the system and it will model it for you. And that's transformers. So transformers are impedance. They're pretty complicated, especially if they can throw you some curveballs when you start adding fans and whatnot. That'll get some people out there in left field. Now the conductors, they'll have a real and reactive component to the whole picture, right? So I can break any conductor down into real and reactive components. And you say, well, why, Tom, is he going over this? Because I don't need to know all this stuff. But the National Electrical Code includes in Chapter 9 a table that gives us this information. And if you don't understand why it's there, you won't understand how to use it. So this table gives you ohms per kilometer or ohms per 1,000 feet, depending upon where you are in the country and the world. The size is down the left. This is our this is our reactance, the hypotenuse of the situation. So this is our X, and you'll notice that it changes based upon if it's in PVC or if it's in steel. Remember to use the right value. So remember, the top value is kilometers and the bottom value is feet. So don't screw that one up. If you're given, I have 300 feet, don't use the kilometers. Believe me, I've been there, done it. And then you have all the resistance for DC and AC. So you got to remember, you got to know if you're, or you have copper or aluminum. I spoke there. So you'll have to tell the difference if your conductor is copper or aluminum. And the resistance values, you'll notice for the most part, they're almost all the same. I think some of the larger conductors will have a different resistance value based upon PVC, aluminum conduit, or steel conduit. But they'll change. Now over here on the right-hand side, they give you an effective Z. Remember, that's the hypotenuse, and they'll use this value to do a lot of voltage drop studies because it's the longer of the three, and it'll get you out of a problem. You can't do a calculation based upon that Z and end up with a voltage drop greater than what you've calculated because it'll give you the worst case because it's the longer portion of that triangle. Okay, so note number one, conductor impedance. This is the note to that conductor. They'll tell you some of the conditions on that, but it's note number 2, which tells us how we have used the effective Z, which is, again, R cosine theta plus X sine theta. So if you think, boy, you know what, I'm not going to need to know that power triangle, you really should understand it, even if you're an electrical contractor or electrician. If you're applying the code and you want to understand, you're doing voltage drop calculations, please, I think it's important to understand this information. So, but if you understand that triangle, you'll understand these notes when it comes to conductors. So I just do an example here. Give me the impedance of a 200 foot length of 2-watt aluminum conductor in PVC. Here's how we use the table. I know my 2 watts, so I isolate that row in the code. I will pick the bottom number for the X part, which is 0.043. I'll use the bottom number in the resistance for aluminum because I said it's aluminum, which is 0.16. And then I do the math. I have to convert the length of the conductor and multiply that. Remember, that's per ohms per 1,000 foot. So I have to take that number times 200 divided by 1,000, and that gives me my actual ohms for a 200-foot run of that conductor. 0.032 plus J, 0.0086. Those are small numbers. You need a lot of that conductor to reduce the fault current. So remember, that is what we break a conductor down into, the real and reactive components. And table 9 is your reference for that. So each conductor, you're going to need to know the size, whether it's copper or aluminum. You're going to need to know if it's a 3 or 4 conductor in one sheath. You're going to need to know if it's how many in parallel and the length of that conductor. And all of that information, we put that into the software applications to give us cable size and conductors in parallel and the length of the conductor. I can select if it's copper, magnetic, duct material, the insulation type, all that good stuff, and enter that information to calculate in my calculations. They play a key role in the power system. They can either reduce or increase fault current. If I put more in parallel, I can increase the fault current. If I add more length of the run, I will decrease the fault current. Remember, you should continue to repeat and update your study and anytime, because if I add more motors to my system, I can increase fault currents. If I subtract motors from my system, I will reduce fault currents. All of that makes a difference in your power system. So what I'm going to do right now is I'm going to take a quick look at I'm going to take a quick look at the chat sessions. I haven't had it open because I had to start and restart it. So I'm going to take a quick look at chat sessions because we're getting down to my YouTube channel. I see that it's I'll put that down. I'll put that down. It's if you search my name, Thomas Dimitrovich, it's youtube.com/C as in Charlie /Thomas Dimitrovich. That's how you can get to my YouTube channel. Please, if you like it, or I'm new to this whole thing. I think you subscribe, and you'll see all of my stuff and what I put in the future. Just as an FYI, Duke Power. So that's private. Arizona's have documents to identify the available fault current. So this is another one. So Jeff Fecteau gave me some information that his utility out in the Carolinas or down in the Carolinas also, they have documentation. So you can always leverage the information from the utilities that they have online, but I still always say call the utility, because the issue that I have is I don't know if I'm on secondary network, and sometimes it's hard to read what those transformers are out there. So it never hurts to call the utility. Series combinations are based on the manufacturer's testing with a question mark. This can't be an Eaton main circuit breaker combined with a Schneider MCC buckets. Very good point. When you get into series ratings, I test overcurrent devices together. So if you're looking at my products from an Eaton perspective, I'll have my circuit breakers upstream of my circuit breakers. I'll have my fuses upstream of my circuit breakers. You will never have a fuse downstream in a series rated pair. They will always have a fuse upstream. You can have a fuse or a breaker upstream, and you will always have a breaker downstream in series rated pairs. And those are tested in a lab. So I'm not testing my breakers with other people's breakers. You're going to series rate my stuff with my stuff. Now, fuses, on the other hand, the way that testing is done, they test with what they call a dummy fuse, or and I drew a blank the terminology there, but in any case, it's a worst case fuse, so that if in a series rated system, they'll say a class J fuse. It could be anybody's class J fuse upstream. So that's just another area of compatibility. On the fuse side, we usually deal with those umbrella fuses. See, I knew I was going to get it. Umbrella fuses, so that I can use any manufacturer's fuse upstream. On the breaker side of the business, though, it's very specific on who I'm testing with. Thank you, Joe. Joe's out there chatting away on the chat. So if those who are dialed in on WebEx, possibly, but only for those on YouTube, the fault current is really low. In general, when you have series ratings, the upstream overcurrent device will open to protect the downstream circuit breaker. Selective coordination is only when the downstream overcurrent device opens in the upstream. Right. So if I have a series rated system, I don't have a selectively coordinated system. What happens in a series? Remember, both of those overcurrent devices are going to open, and when that occurs, it defeats the whole purpose of selective coordination. So remember, tomorrow is going to be selective coordination. If you're unsure of what that is and the impact on system equipment ratings, you're going to want to join that conversation as well. Somebody said they lost me. The series combinations are based on the manufacturer's testing. Yes. So I'm just going through the chat session here. Is there a way to achieve series ratings and selective coordination? If anybody, so I'm not aware of a way to do that. I don't believe that is possible. If somebody says they are doing that, I would highly question the information. If you a 2-odd example, also proper bracing of bus as well. Yes, bracing of bus and equipment. That's why listed equipment is really important. Bracing of the equipment, they all will. I can have a circuit breaker hold its contacts closed for 30 cycles. That video that we saw was 1 cycle, and you saw the magnetic forces. That is a big difference. And when I'm holding those contacts closed for 30 cycles, I'm bringing Lou Ferrigno to the job, baby. Those are big boys. Power circuit breakers, and we're going to learn more about overcurrent devices tomorrow. But your power breakers are beefy because they have to hold those contacts closed for a long period of time. So maybe identify the interrupting rating of the device in the equipment, maybe higher. All right, so please mute your phones. I remember that code, also known as a rapid catastrophic. Okay, so let's take a look on the YouTube side of the business. What kind of comments have come? Will the 10% impedance apply for as-built conditions when performing arc flash hazard analysis? Yeah, because remember, even in the as-built phase, if I look at a piece of equipment and it's labeled 5%, it's labeled by the manufacturer 5%, but the standards permit a plus or minus 10% on that label. So it's going to be impacted in your as-built. So even your as-built, you're going to have to consider that plus or minus 10%. I saw somebody said, I missed the beginning of this class, available on demand after the live session. It will be available on the YouTube session. So you'll be able to go to my YouTube channel. Remember, it's youtube.com/C as in Charlie /Thomas A. Dimitrovich. I should probably put that on this somewhere. All right, so I don't have subtitles. I don't do it. I didn't, maybe in the future I'll have other than English for you. So thank you for dialing in, though. Okay, so let's go back, and what I'm going to do now for the last, it's 2 minutes. I didn't get into the Bussmann FC squared, but I will have a separate section on Bussmann FC squared. I know that for the 2-hour session, here's what I do want to do. Go to your computers. Go to your computers, and I want you to answer, go to menti.com. This is just a quick question. I'm going to have just a quick slide. This is not going to be the CEU credit stuff. This is going to be live. I want to get some feedback for you. I think I have like 4 questions, and then I'll let everybody go. If you go to either on your cell phone or another little window, answer the questions here. I want to get a feeling for what you're doing and whether or not I'm doing the right things here, and timing as well. I know some of us are stuck in the house. Some of us are actually doing out there working too. So the first question is, is this material just right? Is it too easy? Is it too hard? I want to make sure I get the level of expectations here. I got one person saying too easy, one player saying too hard, a lot of people saying just right. This is like the bear going into the mama bear. This This one is too soft. This one is too hard. So that's sort of this is, I call this the horse race over here. So we got 42, 44. We got 6 people saying too hard, 2 people saying too easy. Number one, I know that this tool is working. 48, just right. Okay, stay on there because I'm going to go to the next one now. I got a good feeling, so it sounds so far so good. I'm going to throw the next question up there. Now, is the program going too fast, too slow, or just right? I want to make sure that I'm at the right pace, and I know everybody's going to be different. So I have some electrical engineers on side. I have some contractors. I have different levels of knowledge and capability, and sometimes I can go fast, sometimes I can go slow. But I got a lot of people saying just right, so I think I think it's favorable so far. I got 60 now, 14 saying too fast. All right, I'm going to take that to heed because even I care about the 19 of you as well. Okay, 63. Let's do the next one. Now, this is time period, so I'm trying to get feedback. I've only gotten one person to say they didn't like the 2-hour bit. Let me know where your head's at. Do you like the 2 hours versus 1 hour versus 30 minutes? And what I could possibly do is I might still, if I have a lot of people like the 2 hours, I'll still do the 2 hours. For those of you who like the 1 hour sessions, I will add and supplement some 1 hour sessions. 1.5 hours. I'm surprised that as many people like the 2 hour session. It's good. It's good to know. It's good to know. It's hard to condense. I mean, I still had some slides on the Bussmann FC Squared app, which is a free app. I was going to walk through that with you. I didn't have time to do that. Talk too much. Okay, so let's do the next one. Time of day. So I do this at 12 o'clock Eastern time. I eat into my lunch for an hour, and I eat into your lunch for an hour, and beyond an hour. So enter this in your time zone. I'm going to get your time zone on the next question because you're going to tell me the city and state you're in. So if you like this at lunch your time, then let me know. Okay, most people like the lunchtime, starting at lunch, 29 people. Morning, 50. So you're either morning people or you're afternoon people. Very few in the evening. I told my wife I was going to do this from 7 to 9, and she's sort of like, you're going to do what? And we like I'm at home now. I'm not as traveling as much, which I'm starting to like this stuff, actually. Being at home is a good thing. Okay, so 66 people. So it looks like the not lunch, this platform is working good. And all right, so let's go to the last question. What city and state are you in? And this, just enter your information. That'll give me a flavor for where you're at. And I'm not sure. There, yeah, okay. So Evansville, Indiana, Greenbelt, Maryland, Quincy. I know. Quincy, Illinois, Atlanta, Georgia. Wow, look at this. Nicaragua. I'm international. You believe this? I'm international. Nicaragua. Thank you. Thank you for Costa Rica. That's so sweet. Orlando. I used to live in Tampa, Florida, or St. Pete, actually. I worked for a contract for Florida Power. Crystal River Unit 3, they're taking that down. Philadelphia. Shout out to my boys in Local 98. Thank you. And everybody else in Philly. Milford, New Hampshire. Butler, Pennsylvania. Edwardsville, Illinois. Cannonsburg. Costa Rica. Excellent. Columbus, Ohio. Nobody in Pittsburgh, Pennsylvania. 74 respondents. Sort of get the gist. I don't think they're all shown. Okay, so minimize that. And I'm going to now put up the final slide that if you were sticking around for for professional development hours, what I'm going to need you to do is go to that same menti.com and you're going to enter 20, 17, and 19. Enter your information. And like I did last time, I'm going to have a share drive out there on the web that you can go to and just pick your name and download your file that has your Adobe file. So I'm going to figure out a way to do this on YouTube as well. Right now, I have everything in my WebEx. So don't have a way to register those who joined the YouTube video ahead of time. I'm going to try to figure out how to do that as I move through the week. But remember, check out my www.youtube.com/C as in Charlie/Thomas Domitrovich. And you can actually click on my future videos and see that information. So and be able to not like, but you can obviously subscribe to my YouTube channel, but you can get a notification of when the next event or all the future events. I'm going to plan on doing 2017 code changes and 2020 code changes. Somebody asked for 2017. My buddy's up in New York. I know there are a lot of people on the 17 code, but I will hit both of those. I'll hit the 2017 changes. I'm going to hit the 2020 code changes. And I'm also going to do, again, tomorrow selective coordination. Wednesday is GFCIs. Thursday is AFCIs, arc fault circuit interrupters, and Friday is electrical safe work practices. So for those of you on YouTube, thank you for dialing in and watching this. Again, it's going to be available, and the program is now over. Mark those numbers down, 2017-19 for those on WebEx. For those of you on YouTube, I'm going to fade to the outro.